Hi, today we're going to be talking about section 2.4, which is called solution sets, but it turns out that what we're going to do to characterize the solution sets is take a look at the homogeneous equations. So go ahead and get section 2.4 open and make sure that you get MATLAB open so you can be ready to practice. And remember, you can take notes in MATLAB if you remember to save your notebook when done. Okay, so I'm assuming that you have everything set up, that you have access to MATLAB and you have access to section 2.4 in the online notes. And so what are the homogeneous equations I'm talking about? All right, the homogeneous equations are the set of equations given by the matrix A times the vector x equals the vector 0, the 0 vector. Okay, why do we care? Well, um, it turns out that we can characterize the solution set um, completely knowing the solution to the homogeneous equations. Okay, and it also turns out in the next section it will tell us something about linear independence, which I'm not going to define right this second, but we'll learn about in the next video. Now, what we're going to do is we're going to create the augmented matrix with the vector A and the 0 vector, and we're going to row reduce and solve it. That's going to produce all the information that we need. Okay, so we're going to start with this matrix, and this is the one that's in the notes. The top row 5, 2, -1, and 4. The second row 5, -2, 0, and -2. And we're going to create the augmented matrix and we're going to solve it. So I've switched over here to MATLAB, and what we're trying to do is solve these guys. That's the homogeneous equations. So we're going to create the augmented matrix A, comma 0 vector. Okay, so this is going to get the matrix A in here. And notice I did copy these out of the notes. All right, and the 0 vector I'm calling 0 is just two zeros. And when I do A equals 0, comma 0, you can see, sorry, you can't because I have the wrong thing selected. Let me go here. I'm sorry. And let me run section and see if we can get, oh, so these are not, I have, if you notice, I have semicolons at the end. So when you do that, it suppresses the output. And that is not what we want to have happen. Sorry about that. It took me a second to figure out what setting I had screwed up. But what I've done is I've augmented the matrix, created little matrix A to work with, and I can row reduce, and I have placed the 0 vector right on the end, right? So this is how I created the 0 vector. I just separated the zeros by semicolons, as many of them as I needed. Getting rid of the ink, let me say something. So those of you who have not quite figured out how to switch back and forth between text and code block C, because what I need right now is I need some code blocks. I need some space in here to work. Okay, and it turns out that if I hit the Alt button and hold it down and then hit Enter, it will switch for me into a code block. And it'll take a code block and it'll switch back to text. So I'm holding down the Alt key and hitting Enter to do that toggle switch. And that works on a PC machine. Right. And what am I doing? I'm trying to row reduce little a. Okay, so I've got this little matrix A. And what I want to do? Well, the very first thing I want to do is I'm going to accept that the top row has a pivot in the leftmost column. I'm going to leave that 5 alone. I want to get a 0 right below it. And how's that going to work? Well, I'm going to take the second row and I'm going to replace it with the difference between the first and second row, right? So and we generally have been doing it like this, that the second row equals the second row minus the first row. Right, I just need the difference. Why? Well, -5 plus 5 will equal 0, and I don't really care after that point that what happens to the other values. Okay, let me get rid of the ink so I can see what I did. You'll notice that instead of a colon, I have a semicolon. So I was trying to hit shift to get the semicolon and did not. Hang on. And then I was trying to use a hotkey to run it all. Sorry. I'll, I'll go back and click on the run section. And that fixed the error. So yeah, I'm making some errors this morning. That's exciting. What do we know here? Okay. Well, we have our second pivot. We are in REF, all right? So I have two pivots. And the second one is to the right. It's the second pivot. The pivot in the second row is in a column that's to the right of the pivot in the first row. And I have zeros below them. And all non-zero, I mean, all rows of all zeros are at the bottom. We don't have any of those. So yeah, this is an REF form, which means we can solve it, right? We can solve for what the basic variables are, that's x sub 1 and x sub 2, in terms of what the free variables are, x sub 3 and x sub 4. Okay, so we've row reduced to REF, and so we can grab this second equation and solve it, right? So the basic variables, we have minus 4x2, sorry, minus 4x2, plus, oh, sorry. Okay, so minus 4x2 plus x3 minus 6x4 equals 0, right? Remember, this is an augmented matrix, so we have an equal sign here, right? We normally put the vertical line in the matrix, right, if we were doing this by hand, okay? And yes, we can solve that. And by the way, that is solved for us over here. Let me get rid of the ink. And you can see, right, that we've taken the equal sign and push some things over already. And that one that we're working on, we can divide through by the 4. Okay. And so x sub 2, this is a basic variable because it corresponds to a pivot, as is x sub 1, which is a basic variable, but x sub 3 and x sub 4 are free variables, okay? And we can take x sub 2 and we can substitute in for x sub 2 in the first equation once we have a value for it, okay? And so all this algebra is shown on the online notes, so I'm not going to go through it, except to say that we end up with these solutions. We know that x sub 1 is equal to 1/10 of x sub 3 minus 1/5 of x sub 4, and so forth. We can see we already solved this one. Okay, so what does that mean for us? That means that we're looking for a solution vector x, right? And what equations do we need to be true? Well, for x sub 1, we need x sub 1 to be equal to 1/10 x sub 3 minus 1/5 x sub 4. And what do we know for x sub 2? We've solved for that in terms of the free variables, so we know that it should be 1/4 x sub 3 minus 3/2 x sub 4. And what should x sub 3 be equal to? Well, it's a free variable. It's just going to be equal to itself, as is x sub 4. Okay, so we can turn this into vectors. Let me get rid of the ink and start again. Right? So the 1/10, the 1/4, the 1, and the 0, these are the coefficients of x sub 3. So we have 1/10, 1/4, 1, and 0. And of course, we have the coefficients of the x sub 4 variable. Here's x sub 4, so we have the minus 1/5, the minus 3/2, the 0, and the 1. Okay, so now that puts the solution in vector form. And what does it mean? Okay, we're looking for a solution x, solution vector x, that has this format. It's equal to this. Okay, what does that mean? It means that any solution that we have has to be a linear combination of two vectors, this one and this one, right? Linear combination, well, this is just a real number. X sub 3 is just some real number. Again, it's possible to have complex numbers in a matrix, so this is actually a scalar, but for our class, this is just a real number. So what do I have here? In this red rectangle, we have a linear combination of two vectors. Okay, and the two vectors are based on the two free variables. How do we know there are two vectors? Because we had two free variables. All right, and then we can go into MATLAB and we can actually do our REF, right? And and notice that we chose a linear combination of u and v. Okay, so these are the solution vectors. Sorry, let me make it more clear, all right? So what I did here is I created a vector u, right? And I created a vector v, which is right here. Okay, so u and v are the two vectors we found. And so then what I'm showing you here is that a solution vector, a solution to the system of equations, is a linear combination of u and v. So 2 times u plus 4 times v, and I take that, so that is the vector x, right? I have a linear combination of u and v as my solution x. And then when I multiply a times the vector x, I do in fact get the 0 vector. And because a times the vector x equals the 0 vector, and that's true for all linear combinations of u and v, and you can try more, right? And again, right here, you can click on the upper right corner of that of these things in the online notes, and you can try it yourself, and you can see that the solution set for the homogeneous equations is the span of these two vectors u and v. The span is every possible linear combination of u and v. And therefore, we know that the solution set has two dimensions. Why? Because there were two vectors, u and v. Why? Because there were two free variables. All right. So the basic variables, we're going to solve for the basic variables in terms of the free variables. So the number of free variables is going to be the dimension of our solution space. Okay, and let's take a look at the next example. I'll get rid of the ink, right? And, right, the dimension of the subspace containing the solution set has dimension equal to the number of free variables in the system. Okay? So we have a 3 by 6 coefficient matrix, and so we row reduce it. Let me get rid of the ink, and then we'll scroll down where we can see this row reduction happen. Okay? And what do we know? Well, there are 3 pivots is the first thing to notice. Those are basic variables, so 3 of the 6 variables are basic. And again, more to the point, that means we have 6 minus 3 free variables. And for each one of these free variables, right, x sub 4 and x sub 5 and x sub 6, for each one of those, we have a vector that's multiplied by that real number, by that scalar. So since we have 3 free variables, the solution set of the homogeneous system will be of dimension 3. We'll have one dimension for each of those vectors. And then any linear combination of those 3 vectors will be a solution.